Good afternoon, everyone. My name is Megan Reid. My mentor is Adam Varan, and I work in the Magnet Science and Technology Department here at the MagLab, where we focus on building the world's strongest magnets. So in 2017, the MagLab broke the world record for strongest all superconducting magnet with 32 Tesla. And now we are designing and testing technology to build the 40T. So my REU project this summer has been designing a setup to test the performance of a superconducting flexible lead section that would be used on future 40T test coils. A flexible lead or a current lead is essentially a device that carries current from a power source like a power supply to the magnet itself. This flexible lead that I tested this summer was soldered into 2 copper blocks, which could only move vertically relative to each other inside this flex test box. So for my test, it consisted of finding the initial critical current of the lead, which is the max amount of current the lead can carry before it stops being superconducting, and then moving the current lead by a set displacement like 50,000 times, and then measuring the critical current again to see if it was damaged during the test. So before I could do any testing, I had to design a bracket to fix one of the copper blocks stationary so that only one could move relative to the other one. And then I also had to take into account the Lorentz magnetic forces that would act on this lead when it was in the 40T test coils. So based on where this flex lead would be placed on the coil, the magnetic field would be roughly 11 Tesla. And then I determined the magnetic force to be about 92 pounds, which is a very significant force. Which I then had to find a way to simulate that force. So I spent several weeks researching and brainstorming ideas of how to simulate this force during my test. And I ended up using AutoCAD Inventor to design a fixture that compresses a spring by a certain distance on the copper block that creates a spring force, which then simulates the magnetic force. With this design, I ran into a problem because there was a lot of friction that was created on this copper block that was moving. So I had to do some research into materials with low coefficients of friction, and I found a material called Teflon, which I was able to use in between the copper block and the spring fixture that reduced the friction force for me to be able to move forward with my test. So during the test, I found the critical current initially, and then I placed the flex lead into a hydraulic test machine that moved the flex lead up by a displacement of 6 millimeters in every cycle while it was in liquid nitrogen. And the liquid nitrogen is what allows the flex lead to be superconducting. And then I measured the critical current every 10,000 cycles during the test to see when or if it became damaged. Damage was considered if the critical current value was less than 98% of its original value. So we see here a graph of all of the different critical current tests that I ran. And then in the table, you can see after 20,000 cycles, that percentage dropped to 87%. So at some point between 10,000 cycles and 20,000 cycles, the flex lead started to be damaged, and then we proceeded with the test. We went forward to 50,000 cycles, but the critical current continued to decrease from that point on. So we concluded that the flex lead that I tested this summer was operational up to 10,000 cycles. But then if we wanted a flex lead that could be operational after 10,000 up to 50,000 cycles, that we would need to explore other options or test different flex lead designs moving forward. So that will be the future of this project moving forward, is testing different designs to see what would work, and then just continuing to design and improve technology for the 40T magnet. So thank you.